Today we are very happy to have Sanjin Benić from Zagreb University, and Sanjin got his PhD from University of Zagreb in 2014, and then he was a postdoc in the University of Tokyo from 2014 to 2016, and Yokohama Institute for Theory Physics in Kyoto from 2017 to 2019. And now in 2019, he got a junior position in the University of Zagreb. He mostly focused on the small x phenomenology and also working in transfer spin and also GPD TMDs. And today he will give us the exclusive production and the polarization of chi3 as the Odderon signature in dyes. Yes, Sanjin, please.
Okay, so everyone can hear me, right?
Yeah.
Okay, good. So I'm very happy for this opportunity, and so to be able to give this presentation. So thank you very much. So my kind of goal is to offer some perspective on the phenomenology of the Odderon in the DIS. And this is coming from a couple of works. So we started doing this last year, and so far we have these 3 works. So I want to talk about these works. So first, I want to introduce the Odderon. So maybe I want to start with Pomeron. So Pomeron is perhaps more familiar. So this Pomeron can be on a simple level has been introduced as a T-channel exchange. So this is a colorless exchange in the T-channel, and it was expected to govern the hadronic cross-sections at very high energy. So Odderon is kind of similar to the Pomeron in this context, that it's also a T-channel exchange, but it doesn't govern the cross-section itself, but the difference in the PP and the PP bar cross-section. So in this sense, the Odderon is the kind of C parity -1 or C odd exchange, and that's why we have this name Odderon. So the introduction of Odderon was in '73, and unlike Pomeron, for more than 50 years, Odderon has been very elusive. In terms of QCD, Pomeron is 2 gluons, and Odderon, or at least a bare Odderon, is 3 gluons. And the gluon colors are contracted with this D factor with this D color factor. You might think, okay, so we understand this colorless 2 gluon propagator, and then why we need to care about it's just another gluon, so it's just 3 gluons. There is some argument for this. So, for example, one, at least I think, interesting argument is that this D color factor, so you can get it starting from 3 colors. So SU2 doesn't work. You can have this factor only for SU3 and higher unitary groups. I think this is an interesting point. Another point is that, coming from the context of small x physics, you imagine the proton to be kind of bunch of color sources that are radiating, and the correlations between these color sources are assumed to be random or Gaussian. So in this context, the Odderon emerges as a kind of a probe of a non-Gaussianity of the proton wave function. So this is another point. And the final point is that so Odderon is not just 3 gluons, so this would be kind of a bare Odderon, but we need to care for QCD radiations, and then you need to take into account all the energy enhancements in the particular diagram, and then you don't have just 3 gluons, but this beautiful structure with ladder pairwise interactions, and these vertical gluons are Regge gluons, and so on. So in fact, this is what I will refer to as Odderon, and Odderon in this context can be understood as a solution of a differential equation called the Bartels-Jaroszewicz-Kwiecinski-Praszczałowicz equation, or BJKP equation, that was constructed in the 80s. So then for this equation, so far two type of solutions were found. One in 97, that's the Janik-Wosiek solution, and this gives an intercept less than 1, so your Odderon amplitude drops with energy. And the other is the Bartels-Lipatov-Vaca solution in 2000, which has the intercept of exactly 1. So these two type of solutions kind of live in different parts of the Hilbert space, so to say, because the BLV Odderon is kind of special. So it has two gluons sitting on the same transverse position, whereas in the Janik-Wosiek solution, if you try to take this coincidence limit, the result is 0. So for our purposes, we will mostly focus on this. Well, we will just focus on this BLV Odderon because this is the Odderon that couples to the dipole that is familiar in the context of the DIS. So I will talk about DIS, so only BLV Odderon matters. And finally, I want to mention that Odderon has been put in a more modern context of this of the colorless condensate framework in this works where, first of all, it was established or verified that the evolution of the Odderon is this BJKP equation, and second, these solutions were also analyzed and understood in this colorless framework. So I will talk about this later on. So now I briefly describe what is known so far concerning the Odderon searches. First of all, recently there's been a big breakthrough precisely by looking at the PP and PP bar cross sections. So this is coming from the result of the Totem and the Zero collaborations, which looked at this difference, and their conclusion is that the Odderon has been discovered in the sense that the effect that they see is more than 5 sigma, and you can kind of have a hint of what they are doing, but by looking at this. So this is one of their money plots. So they are looking at the elastic cross-section as a function of the momentum transfer for PP in red and PP bar in blue, and in this deep to bump region, there is a difference between these two cross-sections. So this was kind of a big news, and several media outlets covered this story. So I will not be talking about hadronic collisions, and well, the simple reason is that in the total cross section or the inelastic cross section, there is not an obvious way to say what would be a hard scale and how to approach this computation from a perturbative perspective. So the question I'm interested in is to ask, can we discover the Odderon in the DIS, which is a more controlled setup, and it offers a more direct access to the Odderon using the degrees of freedom that we know from perturbative QCD. So here I will focus on dominantly on what is a classic channel for the Odderon in the DIS, and this is an exclusive reaction where in the final state you are producing either a meson or a quarkonia with C parity +1. So this is an exclusive process, so you have control over the quantum numbers, including the C parity. So immediately, if you have the C parity of the meson to be +1, you are sensitive to the C odd part of the proton wave function. So just in principle, simply observing this process would be enough to claim that the Odderon has been discovered. So this is a simple point, and in the upcoming slides, the story, of course, gets more complicated. So I will start with light mesons, namely pi0. Pi0 was indeed searched for at HERA in the early 2000s, and this was done in the near photoproduction limit. So the photon is mostly transverse. So they were looking at the excited nucleon in the final state to have the p waves so that it overlaps with the transverse photon. However, this process was not directly observed by these searches, and the H1 collaboration could report only an upper bound on the cross-section of this order. Then similar searches were done also for tensor mesons and resulted also only in upper bounds. At that time, the theory computations, so I'm quoting this paper by Berger, gave cross-sections that were actually order of magnitude larger than this estimate. So it was kind of confusing. And this Odderon search, to my best understanding, was dropped at HERA. Then if you go 10 years later, in the EIC white paper, there is no mention of the Odderon. So of course, in our opinion, Odderon should be considered, and this is what we want to advocate. So I keep here still this discussion a bit on exclusive pi zero, because at low energy this process is actually measured. This is done at Compass and JLab, and here I'm showing a plot of a t-distribution for this cross-section that was presented in the recent Diffraction and Low X conference. So this is preliminary data from Compass, but nevertheless, it just points out that this is just measured. So the low energy region means you are sensitive to the quark part of the proton, and in particular, the physics point of studying this process is to consider helicity flip GPDs, and this is interesting because in the forward limit, this would give you let's say, an independent handle on the transversity PDF. So this is the physics point of studying this process at low energy. But in principle, if you go to high energy, somehow gluons should be important. So there should be a transition to this Odderon state. And is this something that can be measured at the EIC? I think it's an interesting question. Now I move to quarkonia, which is the main point of this work. Well, most of the theoretical work was done for eta C particle. However, this process has not been observed. Eta C has not been observed in an exclusive reaction so far, to my best knowledge. And I think part of the reason for this is that eta C is kind of difficult to detect. It has very small branching ratio to hadronic channels and to gamma-gamma. So it was a theoretical playground, and recent model computations concluded a cross-section that should be around 10 to 100 pentabarns per jet squared at most. So if you want, you can compare this to the limit that was set by HERA. Of course, this is not apple-to-apple comparison because this is eta C, and before we had pi zero. But these more recent model computations seem to point out that there is just a simple reason we haven't seen this process at HERA. It's just that the cross-section is too small. So the main point of our study is to consider chi-C quarkonia. So so chi-C comes in. So it's a family of 3 states: chi-C 0, 1, and 2 in terms of their spins. And these are excited states, so they are p waves. And the advantage with respect to eta C is that they have a nice decay mode to J psi and gamma, so they just decay radiatively to the lower lying quarkonia. And especially for chi-C1, there's a nice branching ratio in this decay mode. And actually, another interesting point is that for chi-C, there is actually data. Now, this data is not what we would like to see, so we want high energy data, but this is data near threshold, and it's a preliminary result coming from the GluX collaboration. So here you see that they were able to see about 50 of chi-C1s, and this is a preliminary and published in these proceedings. And their point or the highlight of this result is actually a t distribution of chi-c was obtained. And they compared the t distribution of chi-c with the t distribution of j-psi. So the t distribution you see on this vertical line for j-psi has a strong slope, whereas in the case of chi-c, so just by changing the quarkonia, the t slope is more or less flat. So they report really a strikingly different t distribution. And again, an interesting point is, well, can something like this, can chi-c also be measured at the EIC? This is what we well, this is the main point of our theoretical study. So to get there, I want to explain some details of the computation. So we are interested in computing the cross-section at high energy, and the appropriate language for this is the so-called dipole framework, where you imagine the incoming photon from the DIS fluctuating into a quark and the anti-quark pair. And these are energetic quarks, and they interact with the target iconally. So the natural description is in the coordinate space, because for the iconal interaction, their transverse position will not change. And so scattering on the target, they only get color rotated, and this color rotation is described in terms of the Wilson lines. So the S matrix for the dipole proton scattering is written here as a kind of a correlator of two Wilson lines. And we can describe it in terms of the dipole size. This is the R variable, and in terms of the impact parameter, that would be the conjugate between the initial and that would be the conjugate to the momentum transfer between the initial and the final state proton. So you can formulate, of course, the very same amplitude also in momentum space, which then depends on the intrinsic KT, that's the conjugate of the dipole size, and the momentum transfer, which I call here delta. And so in this formula, I also keep the spin labels explicit so that there may be also a spin flip that will be important later on. So the way Odderon emerges in this framework is simply as an imaginary part of the dipole S matrix. And you can confirm this by either, so one way to confirm it is by expanding the Wilson lines and finding this cubic in the gluon field. So I make a shorthand for the this longitudinal integral over the gluon pancake alpha. And you have a cubic in the gluon fields that is contracted with this D factor. So this is one way to confirm this is really the Odderon, and another way is to perform the charge conjugation operation. So this would be flipping the quark in the anti-quark position, and then obviously this Odderon amplitude will flip sign. This is the argument that it's C-odd. So this would be a kind of three-level Odderon or bare Odderon, and then if you consider radiative corrections to this object, you get the evolution equation that I was mentioning previously, and I will write this evolution equation now in this more modern context from the colored glass perspective, coming from these works. So first, let me mention that so the dipole, of course, I said imaginary part is the Odderon, and then the real part, that's the Pomeron amplitude. And then if you look at the Odderon evolution, the equation is written here. So you are solving this function as you are finding the solutions as a function of rapidity. So rapidity, this is just log of x, and this is a log of energy, in other words. And this equation contains two pieces. One, so this first linear piece, this is exactly equivalent to the BJKP equation, and therefore it will give you a constant Odderon at asymptotically high energies. However, there is an additional piece coming from the Pomeron-Odderon couplings, and the simple way to understand why this piece is here is because in this framework you don't count gluons. So it means that 3 gluons is Odderon, but also 5 gluons can be Odderon, and 7 gluons can be Odderon, and so on and so on. So then you have these extra terms. And these terms, in fact, act to suppress the Odderon as you go to higher and higher energy or to smaller and smaller x. There's a simple way to understand this. So when scattering is strong, Pomeron is of the order 1. So you just put n and this n and this n to be 1. Then this term cancels this term, roughly speaking, and this term cancels this term. So only this term is left, and this has a negative sign. So this will lead to a suppression of the order. The final remark I want to make before going into more details of the computation is to make a connection with GTMDs. So in fact, if you think about the dipole, this is already a kind of GTMD. It depends on the intrinsic KT, and it also depends on the momentum transfer. And in fact, in this work by Bussari et al., they showed that the dipole distribution can be decomposed into 3 scalar functions, so 3 independent GTMDs in the Eikonal limit. This will be F11, F12, and F13 in the standard nomenclature. And then these are complex functions, and the Odderons are imaginary parts, basically, of these complex functions. So the main point of this work was to emphasize that there is not just one Odderon, there are in fact 3 Odderons coming from imaginary part of each of these functions. And imaginary part of F11, that's usually called G11, that's the so-called spin-independent Odderon. Usually this is the one that's considered in most cases in dipole models, and you can appreciate it as a kind of directed flow due to this cosine correlation. Now, F12 is also very interesting. This is called the spin-dependent Odderon because of this Dirac structure, because in the forward limit, this function is just the gluon-Sivers function, as was emphasized in these works. So in the first part of my talk, I focus on the spin-dependent Odderon, and then in the second part, I show some results for the spin-dependent Odderon. So now I'm coming to the computation. We are, as I said, looking at the exclusive process. This is gamma star p collision, and we are considering center of mass frame in the for the gamma star and p. So the photon is moving dominantly in the minus direction, the proton dominantly in the plus direction, and we are exclusively producing a quarkonia, which I generically denote by H in the final state with momentum delta, and there is a deflected proton that should be detected. Then the helicity amplitude can be formulated as follows. So this is a helicity of the initial photon, and lambda bar is helicity of the produced quarkonia. This is proportional to the Odderon amplitude that is contained in this part of the diagram, and this remaining part that can be understood as an overlap between the photon wave function that is coming from this part and the chi-c wave function that is coming from this part of the diagram. So the goal is to compute this amplitude numerically, and then we need this overlap between the wave functions, and we need the Odderon. So the overlap, so the photon wave function we know, and we need the chi-c wave function. The chi-c wave function, we assume it has this type of structure. So this is generally a non-perturbative object, but we assume this type of spin structure and a scalar function multiplying it, for which we adopt the popular boosted Gaussian ansatz. For the spin structure, we have this vertex for which we choose a covariant ansatz that will change depending on whether we consider the scalar chi-c quarkonia axial vector. Then we have this gamma mu and contracted with the polarization vector. And then the tensor quarkonia has this energy momentum current and the spin to polarization tensor. So once this is given, we can compute this wave function by computing these currents explicitly, and then from this we can get overlaps. So for the overlaps, it is convenient to separate out the delta dependence in the context of this off-forward phase, and the remaining scalar overlaps are just functions of the dipole size, which for the scalar harmonia are very simple, and I show them here. So then we need another step to get the amplitudes. So we plug this back in this formula, and then we expand the Odderon in the Fourier harmonics. And this is the origin of this sum here, and these are the Odderon harmonics. In practice, you have all these harmonics should be taken into account. So sorry, in principle, but in practice, we only take into account the lowest lying modes, namely just O1, K with K equals 0. We check that the higher harmonics are either suppressed by the initial condition or also additionally suppressed by the evolution equation. So we pick up only K equals 0 for numerics. Then we repeat this exercise for axial vector harmonia. Of course, now you have more overlaps to compute, but this is basically done in this paper. And then again, we have to do it for the tensor quarkonia. So this is the most complicated case. So you have 5 polarizations of the tensor and 3 of the photon. That will give you 15 overlaps. And then you have a bunch of amplitudes to compute. And this is all collected in this paper. I will not explain details of this computation. Just I will move on to the final ingredient. That would be the initial condition for the Odderon and its evolution. So the Odderon amplitude, I just repeat what I showed at the beginning of my talk here as imaginary part of the dipole. And then what we do is we expand this dipole to the cubic order. So you have seen this equation as well. That's a cubic in the gluon fields. Then at small x, we can, so these are small x gluons, and we can compute these functions or these operators at this level in terms of the Weizsäcker-Williams approximations, where they are basically sourced by quark density currents. And then at this step, you are basically having a cubic in this density currents sandwiched between the 2 proton states. So this is how it looks in the diagram. So you have these quark densities that are sourcing the small x gluons, and this computation for the quark density operators is performed in the kind of overlap representations that was advocated by this work by Dumitru Miller and Venugopalan, but also this is coming from earlier works, for example, by Brodsky and Schlum. So we are using these quark model wave functions for the proton, and this is how we generate the bare order, let's say. Of course, there are many ways to connect these gluons, but this particular diagram is interesting. Here, each gluon connects to a different quark, and you can kind of intuitively understand that this type of diagram should be important at high T, because each of these gluons can give a high T kick to each of the quarks without actually breaking the proton, because the quarks can move. There's a phase space where the quarks would move in a similar direction, and you can keep the proton in the final state. So this is important because for this intuitive reason, you kind of expect a weak T dependence in the Odderon exchange amplitude. Now, in this model computation, we, of course, just make the computation, and we find the Odderon including its sign. And then by this, using this as an initial condition for the small x evolution, we find that this sign is not changed by the evolution equation. So coming to the evolution equation, if you consider the dipole in a general sense and you make the Fourier expansion, the even harmonics will give you either the angular average Pomeron, the elliptic Wigner, and then the odd harmonics will give you these coefficients A1, A3. So A1 is the directed flow coefficient. I called this earlier O1, now I call it A1. And here is a numerical computation of A1 based on this quark model. And so this is shown as a function of B. And it's coming from these works by Dumitru Mantisari and Patelainen. And the important point to see is that actually the y-axis is multiplied by a factor of 100. So this Odderon directed flow coefficient is really very small, and this will drive the size of the cross-section, of course. So this we use as an initial condition, and then we take this Odderon evolution equation and solve it on a 3D grid that will be in the dipole size, in the impact parameter, and in their relative angle. And now I'm showing the effect of the evolution, but first I will move from B to the momentum transfer. So I make a Fourier transform, and then you are looking at this full blue curve. That is the Fourier transform of this black curve here. And indeed, you can see that this has a rather weak t dependence. So somehow this intuitive picture I mentioned previously seems to be supported. And then, so this is the initial condition. Then as you evolve, the Odderon decreases, and this is coming from the nonlinear corrections in the evolution equation. But interestingly, the slope is not affected by the evolution equation. So with these ingredients, we can compute the cross-section, but still let me make one more remark. And this is concerning the Primakoff process. So what is Primakoff process? So this is basically gamma-gamma fusion. So instead of gamma Odderon fusion, you are picking up a photon from the proton. So you have to, in principle, also take into account this type of QED, a purely QED process, because the photon has the same quantum numbers as the Odderon. So naively, you would say, okay, this is QED process, so this should be small, and you are right. But of course, as I showed you, the Odderon amplitude is itself small. So we should care about this, even about QED corrections in this case. And this is simple to compute. So you just compute the gamma-gamma sub-amplitude, and you multiply with the Dirac and the Pauli form factors to get the full amplitude, and then you can compute the cross-section. So finally, I'm coming to the numerical results. Here I'm showing the t distributions in the gamma star p cross-section for different quarkonia, Chi-C0, Chi-C1, and Chi-C2. And first, let's look at the Odderon contribution. That would be the blue curves that you see here. The Odderon contribution is at the initial condition, that's the full blue curve, and then this dashed and the dotted curves are at lower x or higher in energy. If you look at the Odderon at low t, or let's say going exactly to t equals 0, the Odderon cross-section vanishes, and this is coming from this, basically from the symmetries of the Odderon amplitude, namely this cosine phi modulation. In the low T region, actually the Primakoff process is what dominates, and this is shown in the orange curves here, here, and here, and it's just coming from the Coulomb T. Now, if you then move to the higher T range, then we have this characteristically weak T dependence of the Odderon, and somehow, let's say after T equal 1 Jeff squared, the Odderon cross-section takes over, and it actually dominates. The magenta curves that I'm showing here, this is the total cross-section. That's what supposedly would be measured, and this is where the Primakoff and the Odderon contributions are added in on the amplitude level. And in our computation, based on the microscopic model of the Odderon, we find that these two amplitudes interfere constructively. And then this summed cross-section is above the Primakoff background. So the message of this plot is that, okay, to find the Odderon in this channel, we should look at the moderate to the high T range. And of course, the elephant in the room here is the size of this cross-section. You might have noticed that this cross-section is of the order of 10 to 100 femtobars at most. So comparing to JPSI, of course, JPSI has a very large cross-section, but it's also interesting to compare the T-slope. So the JPSI has a very strong T dependence that is controlled by this slope parameter, which is basically coming from the size of your target. However, if you make the same parameterization or a similar parameterization for the Odderon, then this slope parameter is actually a factor of 4 smaller than in the case of the Pomerov that controls the JPSI. cross-section. So this is an interesting point to contrast these two processes. So but let's move to the main point, or one of the main points is to see whether this process would be feasible to be measured at the EIC. So for that purpose, I'm showing here the total cross-section, and this is now in electroproduction as a function of energy. And I'm employing the standard EIC cuts, but I'm also looking at small x only, and picking up a T-bin where the Odderon contribution becomes important. So here again, the total cross-section is shown in magenta, and roughly the conclusion that you see from these plots is that the electroproduction cross-section is of the order of 10 to 100 femtobarns, okay, depending also on the energy and a bit on the choice of the Chi-C quark-ordinate. So based on this, we made a simple estimate of what would be the expected number of events of Chi-Cs at the EICs. Sorry. So here we assume a detection channel, Chi-C going to J-psi and the gamma. J-psi, of course, is detected through its dilepton decay. And I'm showing here an estimated number of Chi-Cs per month in the 3 different bins of T, low T, let's say mid T, and high T. And the bars, the different bars represent different Chi-Cs. So in this low T bin, we are having about hundreds of Chi-Cs per month. Note that this is, so we turn on all the knobs to the maximum, top EIC energy and top luminosity, and you get about hundreds of Chi-Cs. And these Chi-Cs in the low T range, they are dominantly coming just from the Primakoff cross-section. But still, this is important because you can get kind of constraint on the Chi-C wave functions. The signal, the Odderon signal, you'll start to see in this mid-T range. That would be these magenta bars. Here, the number of events is smaller. You get about a dozen of events, maybe 20 events, depending on the Chi-C state. And the ratio to the background is about factor of 4 in this range. Now, the interesting point is if you move to the high T range, this is not the range that's usually explored in the context of GPT, so it's kind of interesting in the context of the Odderon. You don't pay much price in the number of events, thanks to this weak T dependence of the Odderon amplitude that I mentioned previously. But you just enhance your signal to background ratio, as is seen on this plot here. So this is a top EIC energy, and then if you move to lower energies, let's say 85 JeV, you still get decent counts at mid and high T range. You can get about 10 counts, so this works also there. And then if you go to even lower energies, well, then the number of events drops somewhat. Okay, so now I want to just briefly entertain another possibility. So as you have seen, the way to see the Odderon with proton targets is to consider moderate to high T range. In the low T range, you have this Primakoff background, but also generically the Odderon cross sections are just small. So is there a way to kind of move around these obstacles? One way to suppress the Primakoff background is to change the target from the proton to neutron. And so sometimes this is referred to as target DIS. Of course, you have to use something like a deuteron target and be sure to really have the neutron active in the DIS. But so in principle, with this, you can really strongly suppress the Primakoff background. And this is an example of such a computation where the orange curve is now the Primakoff background, and you can see the Odderon in blue, and the Odderon just dominates even at low T. So this is a way to suppress the Primakoff in principle. The cross-section, on the other hand, can be enhanced by looking at collisions with a nuclear target instead of a proton, which we can also do at the EIC. And some rough estimate. So for a large target, you would expect that the total cross-section has this enhancement factor of 8 to the 4/3, and then you are moving from 10 to 100 femtobarns into 10 to 100 picobarn range. Of course, your Primakoff cross-section will also become enhanced, and of course, you cannot access, or it's very difficult to access the high T range because you have to because you have these incoherent backgrounds that are difficult to suppress. But still, in principle, I think it's kind of interesting to have these options in mind as well. Now, in the remaining part of this talk, I will focus on the forward limit. So here, the spin-independent Odderon decouples. We have seen that the cross-section is just 0 in this limit, and the spin-dependent Odderon takes over. So we have this gluon-Sivers function here in the forward limit. So gluon-Sivers function is usually accessed in transverse polarizations, namely if you just stick a transverse transversely polarized spinner here, you get this famous cross product that's just a hallmark of the single spin asymmetry. And the gluon-Sivers function is basically unknown, and one of the key TMDs that will be explored at the future EIC. The traditional way is to use this single spin asymmetries, but here I want to emphasize that there is another way, as was pointed out in these works, which has the advantage that you can work with unpolarized targets. And if you consider an exclusive process where the proton in the final state with respect to the initial state flips its helicity. This is also sensitive to the gluon-Sivers function, as emphasized in this work. Now, there's a problem with this suggestion, kind of generic one, as you have seen so we are in the forward limit, and in the forward limit, there's a large, basically an infinite background coming from the Primakoff process that's just generated by the Coulomb tail. This would be, for example, in the classic case of exclusive pi zero production. However, there's an exception to this rule, and this is if you consider either an axial meson or an axial quarkonia, such as chi-C1, then you can employ the Landau-Yang selection rule, which says that basically a massive vector particle cannot decay into two on-shell photons. So you can turn this argument around and then look at not only the forward limit, but also the photoproduction limit of the gamma-gamma fusion. And what comes out is that the Primakoff cross-section has now a screened Coulomb tail, and it is just finite in the forward limit. This is a formula that you obtain in the heavy quark limit as well, where this is the derivative of the radial wave function at the origin. So this is interesting because in principle now you don't have infinity to fight against. You have a finite quantity to fight against with the Sivers contribution. And another point that's important because Sivers contribution comes with proton helicity flips, so there is no mixing on the amplitude level with the Primakoff cross-section. So now you can make the same exercise and compute the Sivers cross-section, and here I'm showing the heavy quark limit of this result because I think it's very illustrative, and it is proportional to the gluon-Sivers function squared. Actually, what comes out here is the first moment of the gluon-Sivers function, or this is connected to the tri-gluon Chu-Sterman correlations. But I think this is a beautiful formula, and it's kind of analog to the Riskin formula that we have for J psi. And it's important to emphasize that it's proportional to the square of the gluon-Sivers function, whereas the spin asymmetries are linear in this function. So it's even more sensitive in principle. Okay, so now I want to make a ratio. This will be useful later on of this cross-section and this cross-section, and denote this by small r. And now I want to discuss the polarization of chi-C1. So remember, we are in the photoproduction limit. So the incoming photon is transversely polarized, and in the case of the Primakoff amplitude, this transverse polarization is just transferred to the final state. So the final chi-C1 comes out also transversely polarized. On the other hand, in the Sivers case, the proton flips the helicity, and this then kind of absorbs this transverse polarization of the incoming photon, and the outgoing chi-C1 comes out longitudinally polarized. So in case of Primakov, it's transversely polarized. In case of Sivers, it's longitudinally polarized. So you can appreciate that this can leave a signature in the angular distribution of the decay products of chi-C1. So you put yourself in the rest frame of chi-C1 and look at the angular distribution of the decay. This can be written down in terms of a couple of angular coefficients, and one of them, actually the only one that's non-zero in our computation, is this polar anisotropy coefficient lambda theta that just controls this. It controls this cosine squared modulation. And then in the case when we have only this process, this coefficient is negative, equal to -1/3. And if we have only this process, it's positive. So it means that the angular distribution will change. So it means that so understanding the angular distribution, we can have some signal for the Gluon-Sivers function or the Odderon. So this is the result in the two limits, but in the general case, where both of these terms contribute, then you have this formula that is written down in terms of this R quantity that I introduced in the previous slide. So this is my basically final slide. And here I'm showing the model computation first for this ratio of the cross-section. And so here we are not using some small x model. We are not doing evolution. It's just a computation that's based on what is so far available concerning the models of the Sivers function, and based on these two works. So we have these two models, and the main point here is to emphasize that this ratio can be sizable. So for example, in this 5% model, the ratio is almost 100. So it's kind of like, it can be 30 or so. So this is a logarithmic scale. So it means, in principle, this process could give some constraint on the Gluon-Sivers function. And this is interesting not only in the context of the EIC, but also in the context of LHC, because this is an opportunity for the UPCs, because it's almost photoproduction limit, and also because you don't have to polarize the proton. Then taking this R function, we can compute the anisotropy, the polar anisotropy, and I'm showing here again the results in the two models, and you can see how either as a function of x, you can change sign, or using different models, you can change sign. So this sign change will be a signal of the spin-dependent order as well. And now I want to kind of give some basic conclusions, or challenge, let's say. One, so we are facing this 10 to 100 femtobarns cross-section, at least according to our model estimates. And so this is a challenge for the experimentalists. But hopefully, the EIC, or the high luminosity at the EIC, can help in this regard, and still we can see this cross-section. Then the next point is, well, how about detecting how about detecting ICs? This is something I didn't mention. There will be a feed down from psi to s. So remember, we have a tower of quarkonia states, and just above chi-C we have psi to s. So this can also radiatively decay, and just imagine we don't see this photon, this will the produced chi-Cs in this way will scramble your signal. So of course this cross-section is large, so it's a problem or a challenge if you like. So in this regard, what I can say is that since this is coming from Pomeron, the chi-Cs that would be emerging in this way would have a sharper T spectra, whereas in the case of the Odderon, this T spectra is much milder, and perhaps this could help in disentangling the two sources of chi-C. Finally, from the theoretical perspective, I think it's interesting and important to develop this computation also at lower energies, perhaps from the GTMD or a GPD perspective. So in the context of GPD, the Odderon would be something like a twist 3 GPD. And finally, I think computing exclusive pi zero or making a kind of theory update for exclusive pi zero, I think it's important for the EIC kinematics. And with this, I'm done. So thank you very much. I'm finished.
Thanks for excellent and clear talk. Now it's time for questions.
Yeah, Sanjin, very nice talk. Thank you. And I have a couple questions. So can you go to your cross-section comparison, chi0, chi1, chi2?
Yeah. Here.
Yeah. So chi0 is bigger than chi1, chi2, right? So what's a simple reason for that?
Well, chi0 is similar to chi2, I would say. I don't see it's bigger, at least.
Oh, the following side I think is bigger, right?
Say again?
Oh, okay.
So chi0 and chi2 are similar. And chi1 is kind of special. So for chi1, actually, I showed, but I was too fast maybe. Some of the overlaps are 0. So for example, you don't have an overlap. So starting from longitudinal photon going to longitudinal chi1, this overlap is 0. So this, I think, is connected with the symmetries of the Odderon. So you have this cosine pi modulation. So this is kind of like angular momentum, and so you have to counteract this with the spin of either in the initial state or the spin in the final state. So the L to L, longitudinal to longitudinal transition is a 0 for chi1. And also in the transverse to transverse overlap, you only have the transition where the where the polarization is preserved. So if the polarization of photon and the axial quarkonia is opposite, then this contribution is also 0. I think this is, again, coming from the Odderon, because the Odderon has, I think, just one unit of this kind of conformal angular momentum, whereas here you would need 2, right, to get this spin flip. So I think this could be maybe too simplistic, but could be the reason why some of these overlaps are 0, and therefore why for chi1, where was I here, this cross section is kind of smaller.
Okay, got you. So another question. So the T dependence really coming from the wave function you use for the proton. Is that right?
Yeah, because so you can see it here. So this is the T dependence of the Odderon, and then in the cross section, this is just inherited. So if you look at this curve and the cross section curve, they look basically the same.
Mm-hmm. Because they compute in the whatever Brodsky model for the wave function, right?
Yeah.
That's because your initial and final wave function will have some kind of momentum transfer there. So.
Yeah, exactly.
All right. Okay. Oh, one last question. So can you go to this photo product limit? You have this one nice say that this here. So what's the T dependence? So here you say T equals 0 is constant.
Right. So it's just a constant. So what would be the t dependence if you? Okay. So the t dependence, what I can show is this curve, right? So this is the Primakoff cross section, and so xt.
That's like a that's like a form factor, right? Okay.
Right. So the t dependence comes. Yeah, sorry. The t dependence just comes from the form factor. Exactly. Yeah.
But for Chi0 and Chi1, there's additional 1 over t behavior.
Right. So exactly. So Chi0 and Chi2 have 1 over t, but then for Chi1, the 1 over t from the photon exchange is screened by the remaining parts of the amplitude. So in the remaining part, you find the term that is proportional to t again, and then you just get a constant.
Okay, thank you.
Yeah.
May I have a question? So for the Odderon, if the target is polarized, the Odderon will be more important compared to the unpolarized target.
So
I have the same question actually.
So for polarized case, yeah. So for polarized case, you can consider single spin asymmetries, and this is the way to probe the Gluon-Sivers function. So it's an inclusive process, and you would imagine producing something like heavy quarks T0 or J psi inclusively. So in principle, the inclusive cross section is larger, right? So in that sense, the single spin asymmetry could be maybe the way to see the Odderon in the context of the Gluon-Sivers function. I'm not sure if I answered your question, but
yeah. Okay.
So maybe we can somehow rephrase this question. So you have spin-dependent Odderon. You also have spin-independent Odderon.
Yeah.
Do you have any kind of inequality between these two? And the spin-dependent one should be smaller than the spin-independent one, or not? Or they are just totally different?
Well, I'm not sure. I mean, so it will depend on the kinematics, right? So at t equals 0, it's just these. But at general t, I don't think there's a computation so far. And actually, this is the reason why I'm together with Adrian and other people. I'm working on this computation to try to have a model computation for the spin-dependent Odderon that's based on this quark model approach, and then we can compare with spin-independent and see the magnitude. Okay. I don't have a good intuition whether naively I would say they should be similar. But I don't know. I actually don't know.
Okay. It's more complicated. That's what they say.
Yeah, it's more complicated, but yeah, it's one of the future works.
Do you have a question on that? Okay, maybe we set no questions. Next speaker again.